So, welcome to the virtual lecture on Group 16, the chalcogens. Again, that name is a little more common than pnictogens, which we use for Group 15, but less common than, of course, halogens, which are Group 17. And so, the list of elements are these: oxygen, sulfur, selenium, tellurium, polonium. Oxygen is a colorless gas. Sulfur is a usually yellow solid, but that's actually due to trace impurities. Selenium is a silvery-looking, grayish, metal-looking substance, even though it's actually a non-metal. This is a lustrous silver solid. The tellurium, that is, it's a metalloid. When you get down to polonium, it's a true metal, although all of its isotopes are radioactive, and so there's not a whole lot known about it. This is, of course, one of the two elements that was discovered by Maria Skłodowska, otherwise known as Marie Curie, resulting in a Nobel Prize in chemistry. And so, obviously, one of the most important elements on this list is oxygen. This is the stuff we breathe. It doesn't come as atomic oxygen, as I'm sure you firmly know in nature. It comes as O2. This actually has an interesting historical story to go with it. It was discovered by Joseph Priestley in 1774. Now, obviously, discovered is kind of a loose term. Everybody knew that there was something in the air that was, keeping us alive, but he's the one that quantified it. And what he did was his discovery of the oxygen disproved what was called the phlogiston theory, which had been around for quite some time before that. Georg Ernst Stahl is actually the major proponent of this, and what this theory says is that when things are burned, they lose phlogiston. Of course, what is that? Well, nobody knows, or knew at the time. And when they burn, they became lighter. That just sort of makes sense when you think about this, because if you take a 3-pound, 5-pound log, put it in your fireplace and burn it, the ashes that result are substantially lighter. So according to Stahl and the phlogiston theory, it lost its phlogiston. But this is actually incorrect, because if you combine any substance with oxygen and burn it in a closed container, that stuff will have a higher mass. And so that is what Priestley did in 1774. He disproved the phlogiston theory. This was further confirmed a year later by Antoine Lavoisier in 1775. So, if we look at oxygen, then it's a colorless gas. And you can condense it, and when you do, you get a blue liquid out. That's because the spin state changes from a triplet to a singlet. You don't need to worry about what that means, but you can find pictures of this sort of thing on the internet or videos. Problem with the blue liquid, the liquid oxygen, is it's highly explosive. You can condense it in liquid nitrogen if you happen to have organic solvent or something like that around, and it goes off. It's like having nitroglycerin explode. So it's not something really to mess around with unless you know what you're doing. Almost all elements react with oxygen at room temperature or with heat. there's some exceptions to this. These metals don't. These are what are called the noble metals in relation to the noble gases. They're inert. In fact, these do not have a surface oxide layer on them, as every other metal does. So copper, which is not on the list, but is in the same group as these two, has an oxide surface on it. Gold and silver don't. These are also some of the precious metals. So those in the noble gases, with, well, two exceptions, and we'll see this later on, don't react with oxygen. So one of the things you might also realize, right, is that O2 is an oxidant. The whole process is named after it, in fact. But is it the strongest oxidant on the periodic table? The answer to that is no, it isn't. This one is. Fluorine releases more energy to become fluoride than oxygen does to become oxide. Now, the difference is not that large, but this is definitely a stronger oxidant than O2. So here's a curious thing about that. Let's look at some metal oxides. So we have some element. Let's throw in a little bit of a preview of what we're going to see a little bit later on too. Xenon, which is a noble gas. Now xenon reacts only with two different things. This one, oxygen, or this one, fluorine, doesn't react with much else. And you'll see why that is later on. So what is its highest oxide and what is its highest fluoride? What that means is how many oxygen atoms can you attach, or better yet, what's the highest oxidation state of these elements you could obtain using oxide O2 minus or fluoride F minus. For chromium, the highest oxide is CrO3. Okay, and before we delve into that, the highest fluoride is CrF5. For osmium, you can get osmium tetroxide. Oops. But only heptafluoroosmium, or osmium heptafluoride. And for xenon, that's XeO4 and XeF6. So what does this mean? Well, what are the oxidation states in each of these 6 compounds? Here, it's chromium 6. But here, it's only chromium 5. Here, we have osmium 8, but the fluoride is osmium 7. At the bottom here, you can completely oxidize xenon, but fluorine can only do it the 6 oxidation state. So if fluorine, becoming fluoride, is supposed to be the strongest oxidant on the periodic table, why can that not oxidize chromium all the way to the +6 oxidation state, which is the highest one you can get? Chromium's in group 6. It has 6 electrons to lose. It takes osmium all the way up to its group oxidation state too. Osmium is in group 8. Oxygen does that. Fluorine doesn't. Take xenon also to its group oxidation state of +8. Fluorine doesn't. Why? Oxygen brings out a higher oxidation state than fluorine, meaning it can take things to their group oxidation state. What's the reason for that? Oxygen can form a pi bond. Fluorine can't. And so that's the reason why this occurs. So we can use this compound right here. As an example, if we draw the structure of it, here's what you see. It's a tetrahedral molecule with all 4 oxygens doubly bonded. It's the ability to form this pi bond that allows oxygen to bring out a higher oxidation state than fluorine can, because fluorine can't do this. This is actually a fairly interesting looking material as well. It almost looks like it's a glowing yellow solid. It looks actually like the explosive in the movie The Rock with Sean Connery. And it's used as a starting material for a bunch of osmium compounds. The funny thing about it is that if you get it wet, it'll deposit osmium metal on things, including your corneas, your mucous membranes, and things like that. So it's a little bit challenging to work with. So, we've talked at length of other oxygen compounds. And so let's then move on to the second, probably most important element in this group, sulfur. So sulfur can form a variety of different oxidation states, and these are +2, +4, +6. Of course, sulfide is -2. It forms catenates. It's the second most proficient element on the periodic table at doing this. The first of which, of course, is carbon. Catenates are chains or rings of an element. So if we thought, once again, sulfur is analogous to oxygen, it actually isn't. Although sometimes we represent it this way, this isn't actually its form that occurs in nature. You can make that, but what you have to do is vaporize elemental sulfur and then condense it on a cold finger that's chilled with liquid nitrogen, for example, and you'll get a purple solid, which is this material. Sulfur comes in nature as S8. It's an 8-membered ring. With sulfur-sulfur single bond. So here again we have the same type of thing. Oxygen, being in row 2, likes to form double bonds. 2 bonds with itself as a double bond. whereas sulfur likes to form two bonds to itself, but it does it through single bonds. This is analogous to what we saw with the difference between nitrogen, which is N2, with a triple bond, and phosphorus, which is P4, which is bound to three. The phosphorus is bound to three separate phosphorus atoms through single bonds, three single bonds. There's actually a whole bunch of other forms of the element itself that you can get with ring sizes up to 20 sulfur in there. So sulfur is indeed an important element, and where do we get it from? Well, we, being the United States, and one other country, Poland, in the mines of Tarnobrzeg, have a huge deposit of sulfur. So it's extracted from the ground by the Frasch process. This is what we do in the United States, and also in Poland and anywhere else you would find large deposits. Of course, you know the largest deposit of sulfur that we know of is, it's actually on the moon Io, which is one of the Galilean moons of Jupiter. And if you watch 2010, which is the sequel to 2001, which everybody complains isn't as good, but they're wrong, you actually see this moon depicted cinematographically, and it's covered in sulfur. So the Frasch process is not a chemical process, it's actually a physical one. And what they do is they take superheated water and they shoot it into the ground where there's a sulfur deposit. This water then gets pumped out and it extracts the sulfur after it melts it, and then it's put into large tanks to dry, and you get these large bricks of yellow sulfur. Other countries where they don't have this type of material, don't have a lot of sulfur in the ground, use a different source, and that source is H2S. This is also found, of course, with natural gas deposits. The problem with it is that it's toxic to humans in even low concentrations, and it smells also really bad, which is another side effect of it. So there are many compounds that we make with sulfur, and we'll get to one of the more important ones here in a minute. But like many elements form compounds with oxygen, they do with sulfur as well. So things that are called sulfides would formally have the S2- anion in them. And if you've seen this stuff before, what do you think of when you think of an element sulfide? They're ridiculously insoluble in water. The exceptions are the sulfides of group 1, 2, the ammonium cation, and aluminum 3. Everything else is pretty much insoluble in water. Now, one of the things that's actually kind of interesting about these is that these get hydrolyzed in water. So let's say we have an aqueous solution of sodium sulfide. There's two equilibria that occur in that solution. So hydrolysis means something reacts with water, and this is an equilibrium. but you'll first form hydrogen sulfide anion. This can further hydrolyze to release H2S gas. Both of these lie to the left, but there is, of course, some leading to the right. Now, if you think about Le Chatelier's principle, this is a gas which has evolved out of the solution, therefore that's going to shift this equilibrium to the right. And so what you'll find is if you have a soluble salt of sulfide, so sodium sulfide, lithium sulfide, calcium sulfide, something like that, if you open up the container that contains it, there'll be a rotten egg smell, and that's this. It doesn't happen to an appreciable extent, but a lot of times what people will do to prevent that, a bunch of this being generated, is you add some hydroxide to it. So you put a little bit of sodium hydroxide in with to prevent that. The reason you really want to avoid forming hydrogen sulfide, it is extremely toxic. It's way more toxic than hydrogen cyanide, which is the gas that can cause you to fail your respiratory system. And the difficulty is, of course, that this is a heck of a lot more abundant than HCN. So it's not something that we want to have lying around in large quantities. So what then makes sulfur so important? And the answer to that is H2SO4. This is hydrogen sulfate in its pure form. Put it in water, you get sulfuric acid. Another compound that's important that was mentioned here in passing is sodium sulfite. That's used in paper production a lot. And the reason for that is that this will break down the lignin in wood, so you can turn wood into pulp, which you then can turn into paper. And if you ever lived near a paper processing plant or visited someplace where there is one, you'll notice that it smells really bad. That's because they vent sulfur-containing compounds, a little bit of H2S, in fact, and so at certain times of day, the whole town or area will smell like rotten eggs. So this is an important compound as well. We can focus only on H2SO4 itself. And so how is this made industrially? Well, you start with the elemental sulfur. I'm doing the stoichiometry wrong. If you really wanted to, you could call that S8, but we'll simplify it down to S. If you wanted to do that, just multiply all your coefficients by 8. It's simply combined with oxygen at relatively high temperatures. You get SO2 gas. Now, the problem here is that it's hard to further oxidize this to SO3. And so to do that, you need a catalyst. So we heat that in the presence of a catalyst, and that happens to be vanadium oxide. And so if I asked you why is it harder to oxidize, thermodynamically it's favored, kinetically it's not. This speeds up the kinetics, the activation energy. Then we get SO3, which is the precursor for sulfuric acid. Now you can take this and add it directly to water, and you'll get sulfuric acid out. The problem with that is that reaction is very exothermic. And if you're doing this on a large scale, you're not going to want to do that. So what happens is SO3 gas is combined not with sulfuric acid, but hydrogen sulfate. Notice it's liquid. It's a viscous, colorless liquid. It's not the aqueous form. So here's one of those cases where that subscript there is quite important. And that generates this stuff. It's pyrosulfuric acid is the name. And so there's a couple of advantages here, one of which is you're dealing with a liquid. You can add that much slowly and much more controlled to make the sulfuric acid rather than bubbling a bunch of SO3 through. And then what you do with pyrosulfuric acid is you combine that with water. That gives you your end product. And so it's actually not just this chemical that's important. It's actually it's two conjugate bases that are and so sulfate is used for the extraction of electropositive metals from mixtures or even from aqueous solutions. They can precipitate toxic metals, two of them that are notorious are barium. Barium 2+ is really poisonous. It's a heavy metal. Lead 2+ is as well. And so you can precipitate both of those out of solutions because their salts are very insoluble. The other nice thing about this is that sulfate is not oxidizing or reducing. There are other oxides that are. Nitric acid gives nitrate. Nitrate is an oxidant. Sulfate is not. And the other thing is when you dissolve it into liquid, water or something like that, it doesn't affect the pH very much. The reason for that is that sulfate is the conjugate base of bisulfate, and that's actually a relatively strong acid. Sulfuric acid is the one where both dissociation steps are fairly far to the right. The first one is all the way to the right, the second one is also. So we use these things for extractions and all that sort of thing. There's a lot of sulfates in your household chemicals you'll find as well. So they are produced on a relatively large scale. Sulfuric acid is used in lead acid batteries and things like that. It's used in a bunch of different synthetic processes. It's used as a very strong cleaner, and so if you need to get rid of tarnishes or oxide or carbonate deposits, a lot of times you'll use that in dilute form. So this is going to be long enough for one lecture, and so we'll stop there for today.